Hello and welcome to the class on geological time. I'm Laura Lewis. Yeah, and we're talking about the different stages of geological time. So you may have thinking about why have I got the white cliffs of Dover? Because I always choose to pick the photograph of the first slide to link in with the actual theme of the PowerPoint. So some of you may have seen this. So yeah, this is down in Dover, so south coast of England. So you may across the channel may have seen this or coming back from somewhere. So this is a huge deposit of chalk that was laid down in the Cretaceous time, so a little bit before 65 million years ago. And it's because the sea was so warm that a lot of chalk precipitated out. So it's a bit like a limescale in your kettle. So the calcium carbonate is less soluble in warm water. So this was a huge climatic change, which we'll talk about a little bit more in the next slides. Okay, so let's look at an overview of geological time. I'm just going to move this up a little bit. So we have time split into eons. So the eon is the longest period of time. So the Phanerozoic is the time of life. So it means visible life. The Proterozoic, the Archean and Hadean, could also be known as the Precambrian. So sometimes it's known as the Precambrian if we're talking about in terms of life. So this is Proterozoic means like proto, so first life. So people are always changing, obviously, because new discoveries about when life first formed on the planet. So obviously, it's quite difficult to find the first life because they were obviously single-celled, and they don't leave behind great fossils. If you're single-celled, you have to have a shell or a skeleton. If you're a bit squishy, you don't leave behind a good fossil, generally. So it's a little bit unknown. New discoveries are made every day about that. So yeah, the longest period of time is an eon. Then there's an era. Okay, so yeah, we kind of lump this one together because it's not got much life in it. So the Paleozoic, ancient life, the Mesozoic, middle life, and Cenozoic, more recent life. Okay, and the period, these are probably the ones that you're familiar with, and we'll talk about those a lot more on the next slides. Okay, so you can see some sort of major events. So invertebrates become common. Yeah, talk about more detail. The Permian mass extinction. The Permian mass extinction is the biggest extinction of all time. And then you've got the extinction of the dinosaurs, okay, at the end of the Cretaceous there. Okay, so that's the next slide. So yeah, this is nice visual representation. Okay, this came from a website of an overview, but we're going to go into more detail. That's nice photo. Nice picture. So we're going to start right at the beginning. Okay, we're talking about geologically as well as with life. So formation of the Earth. So at 4.6, 4.5, 4.6. So depending on how you date it, the Earth and the Sun formed. So the Sun formed first in the middle there, and around the Sun there was a disk of gas and dust, and this coalesced to form the planets that we know. So the Earth is pretty much the same age as the Sun. Okay, 4.6 billion, 4.5, 4.6 billion. And it's thought that the heavier elements, iron, nickel, or the metals, stayed nearer the Sun, and the lighter materials sort of blown out by the solar wind. It's also sort of gas that the Sun emits and radiation the Sun emits. So the inner planets, so Mercury, Venus, Earth, and Mars, that they've got iron and nickel cores to them, whereas the outer planets, also known as the gas giants, that they've got a lot of gaseous material. They've probably got a solid core, rock, but they've also got huge atmospheres of, in the case of Jupiter and Saturn, hydrogen and helium. In the case of Uranus and Neptune, methane. It's because that it's much colder further away from the Sun, and those gases actually condense and they form an atmosphere. Okay, so the Moon is another huge milestone in the history of the Earth and geological history of the Earth. So how the Moon formed. So the Earth was still young and molten. So proto-Earth. So Earth was molten, like that, covered in lava. So a Mars-sized body, we don't know if it was Mars, but sometimes we use a picture of Mars to represent it, crashed into the molten Earth. And this sent a lot of debris out, flying out of the planet. And this first of all formed rings around the planet, so that would have been pretty interesting to look at, which then coalesced, so came together to form our Moon. So we actually know this because people have brought rocks back from the moon, and they're similar to rocks on Earth. So it's very likely that the moon rocks, or the moon, actually came from the Earth. But they're made from the same materials. And actually, when the moon first formed, it was very close to the Earth, like this picture here, and it would have appeared huge in the sky of the early Earth. And also, to make things even more interesting, the Earth was spinning faster, so days were shorter back then. So a shorter day, and the moon would have been huge in the sky. So that would have been interesting for anything looking at that. It would have been a really interesting time of the Earth to see what that's happening. Unfortunately, we don't think anything was around back then, but it would be interesting to go back in time and see that. Okay, so how do we actually know? How do we know how old the rocks are? So how do we actually know that? Okay, so there's a way of dating called radiometric dating. So certain radioactive materials break down by radioactive decay. So they change from the parent or the original element into the broken down version or the daughter element, a different element. So uranium commonly turns into lead. So these are uranium isotopes, and they both turn into lead, okay, over time. And if you look at their what's called a half-life, so how long it takes for half of it to decay, it's in the region of billions of years. So you can use this to date the Earth. So the idea of it is that when the rock was first formed, it was all uranium. There was a certain amount of uranium in the rock, okay, and over time, more lead is produced, okay, and more lead is produced compared to uranium. So after quite a few half-lives, okay, that there's not much uranium left, a lot of lead. So the more lead there is compared to uranium, okay, then that's how old the rock is. So, and we can use scientific instruments to tell us how much lead and how much uranium is in it, and then look at the half-life, okay, so if there's half remaining of uranium-238, that the rock is 4.47 billion years old, and if it was a quarter, that would be 2.27. So they don't have to really understand that completely to understand the point, but we can measure how old they are by radiometric dating. So this is a graph that helps us. So number of parent atoms, so it's in blue, so it goes down over time. Number of daughter atoms goes up over time. So it's the relative amounts of the original and the daughter, or the decayed element, tells us how old the rock is. Okay, so yeah, so the more broken down element, the more lead there is compared to uranium, the older it is, so the more time has passed. Okay, there's also another way of doing this called index fossils. So we may have used radiometric dating to find different ages of rocks, but also that there's lots of life that can help us as well. These coiled shells are called ammonites. They're used as an index fossil because they evolved very quickly. Okay, there's lots of different types and varieties. They've all got different shells. And for example, that this type could have lived or could have been around for 1 million years. Okay, so if this fossil was found in the Jurassic period in England, and someone found this fossil in France, for example, they know that that's a Jurassic rock, and you can date it within 1 million years just by looking at a fossil. I know it sounds a long time, million, but that's actually quite exact in terms of a few billion years. It's quite exact. So yeah, you have to pick a fossil that only was around for a sort of a short period of time geologically. Otherwise, if it was around the whole time, it's a bit useless. So it could be any age. So that's a type of it's called a rugose coal. So lots of different varieties. But ammonites, because they evolved very quickly, so they changed over one species evolved into a different species over a million years instead of millions. Then they're very good as an index fossil. So ammonites were like an octopus in a shell. They're cephalopods. Okay, a little bit like a nautilus today, if you look that up. Okay, so let's look at some of the periods. So the Cambrian. Okay, so the Cambrian period. So before the Cambrian, there were quite simple forms of life. These may look like plants, but they're actually animals. So Charnia, it's known as. And there's Dicksonia, Dickinsonia. Okay, It could grow to more than 1 meter. So this is something called just before the Cambrian, something called the Ediacaran. So it's like a very small period of time. So rocks are found out in the out in the mountains and things, literally one on top of the other, and one rock would have really simple organisms, and the next few centimeters above it, so the newer sort of deposit would have all of these different types. That's why it's called the Cambrian explosion, because life just diversified very, very quickly. And you had things like Marella. It's an arthropod, so it's a relative of insects and crabs, lobsters and things like that. It kind of looks a little bit like that, kind of with its sort of whiskers like a lobster has. There's a Nomlocaris, which was was by the standards of the time, okay, so over 500 million years ago, it was a huge predator. Okay, so these animals didn't have any eyes or anything, and then suddenly, less than a few million years later, it seems, okay, eyes, complex eyes, okay, developed, and this was Nomlocaris means strange shrimp, because it's a relative of shrimps, and that it actually was found in different parts. So, for example, these front sort of limbs were found in different fossils to these, and then maybe like an eye was found, and then they thought it was different animals, and then somebody found a whole one. It was like, oh, okay, so it's all the same animal. That's happens quite often in paleontology, actually. So it was a strange shrimp, and this is interesting. This little animal called Pikaia is interesting because it is our ancient ancestor. It's the first fossil found. It's what's called a notochord. So that's a primitive backbone. Okay, so stiff internal rod. So these animals didn't have these. These definitely didn't. So we are vertebrates, and so that's our ancient ancestor. A long, long time ago. All related to probably most likely related to, unless someone found a different fossil, earlier one, Pikaia, was our ancient relative. Okay, let's go to the next slide. So next came the Ordovician. So really life diversified even more. Okay, marine invertebrates like the Orthoceras. So there's a big version of that, Orthoceras, which is a squid in a shell. Lots of octopus squid in shells lived in the sea, and trilobites began to exist. So you may have seen a fossil of a trilobite. It looks like a big woodlouse. And the ancestors of insects, arthropods, started to colonize land. So before this, there were just animals in the ocean. Okay, before that. And early land plants appeared on the surface. So actually animals were around before plants, bizarrely. Okay, Silurian was next. So you may not have heard about these eras, so I think it's quite interesting to know about these because they're not quite glorified, are they, in books and things? So in the Silurian, life became more varied, in the ocean. So you see these primitive fish started to evolve. So again, they are our ancestors as well. Fish, and because they've got skeletons, they've got a backbone. The Orthoceras was still around. Corals and reef ecosystems started to develop, and these things called crinoids were around. So they're actually relative to starfish, and they're still around today, a crinoid. Devonian, also known as the age of the fish. Okay, so the Devonian have many types of fish, including ferocious Dunkleosteus. Okay, a fish with armor plating behind it, armor plating on its head. Okay, so the first groups of animals, the tetrapods, were four-legged reptile-like vertebrates. So these things are crawling up here, called tetrapod. Tetra meaning four legs. And the first winged insects like dragonflies and arachnids, so spiders, started to live on land. So spiders came about then. I don't mind spiders, but other people don't like them much. But they kill flies, so they're very important. The Carboniferous. So you may have heard of this one. It's a bit more well-known. These giant horsetails. Much bigger than the ones around today. These plants called horsetails. So it gained its name from a large deposits of coal formed during this time. So if you have coal in your fire, it formed in the Carboniferous. So about 300 million years ago, it formed. So the wet, humid conditions were ideal for life to grow in the swamps. And oxygen levels were also high. Because always a huge explosion of plant life in the Carboniferous caused plants to grow huge. Okay, like they weren't trees as such. They weren't trees that actually hadn't evolved yet. They were different types of ferns that grew into huge trees. And when they died, they fell into the swamps and were buried by sediment and sand and mud. And over time, were compressed to form rock, and rock that we know as coal. So it's carbon. It's actually made of plants and coal. So giant insects. like dragonflies, and nearly a metre long were common. Okay, because they had a lot more oxygen, so they could grow bigger. In the Permian, so you may have seen this type of dinosaur. Well, I say dinosaur in quotation mark because it's not a dinosaur. Dimetrodon. It looks like one, but it actually was a type of animal called a synapsid. So actually, it's kind of a cross between a mammal and a reptile. Okay, so the Permian saw lots of diverse land on Earth. At the end of this period, there's a huge, or the Earth's biggest mass extinction at the end of the Permian. So trilobites die out. Okay, trilobites die out at the end of the period, but modern conifers start to appear on land. Okay, so Christmas trees start to evolve in the Permian. Okay, the Mesozoic. This is when it gets all the glamour. Okay, but really, this one there wasn't quite as much change as the other periods. Actually, I know because the dinosaurs are a bit more kind of well-known animals. So actually, all the dinosaurs you see in things like Jurassic Park weren't around at the same time. I know it's science fiction and obviously artistic license. Obviously, I do enjoy the film. But if you look here, Stegosaurus was in the Jurassic, so that's allowed in Jurassic Park, Stegosaurus. But lots of things like Tyrannosaurus, Triceratops didn't appear until the late Cretaceous. So there was a lot of time between when a Stegosaurus lived, or a Brachiosaurus, and a Tyrannosaurus rex. So actually, an interesting fact is that Stegosaurus and Tyrannosaurus were further apart in time of when they lived than Tyrannosaurus to humans. Okay, this was a larger amount of time between Stegosaurus and Tyrannosaurus than Tyrannosaurus and the humans. Okay, so in reality, that they would have never met each other. Okay, so I know it's obviously science fiction artistic license on that, but just if you want to be let's say exact, Iguanodon was in the middle of the Cretaceous, one of my favorite dinosaurs. Iguanodon, it's huge. Okay, found in the UK in the Isle of Wight. Okay, but it's an amazing dinosaur, Iguanodon. You see a fossil of it. So the Triassic, the first types of dinosaurs, quite small ones, evolved. We get the huge kind of sauropods in the sort of the long-necked dinosaurs in the Jurassic, and then they diversified even more to the huge amount of dinosaurs in the late Cretaceous. And unfortunately, 65 million years ago, at the end of this period, they all became extinct, unfortunately. And also many marine creatures did as well. So things like the ammonites also became extinct as well. So lots of marine life, went with it as well. Probably due to meteorite impacts, so suddenly blotting out the sun and causing huge climatic change across the Earth. But still other life lived on, so it didn't kill everything. This gave rise to the Cenozoic. Okay, so the Paleogene, Neogene, and Quaternary. So after lots of the reptiles and the dinosaurs died out, because not all the reptiles obviously still let them stay, like the crocodiles and the tortoises and things like that still lived on. Okay, mammals gained an opportunity to take over the land, become a dominant species. Because the climate was cooler, the warm-blooded mammals, with their fur and their hair, had an advantage. Okay, so this sort of long period is split up by ice ages, so intermittent ice ages, broken up by very warm periods. So the Quaternary is the age of the, sorry, I just sort of lost the screen then. So was the age of the 4 ice ages, okay? And the woolly mammoth and rhino were common on the in Europe until the end of the ice age 12,000 years ago. Obviously the saber-toothed cats were around as well. So humans would have seen these because humans have been around. So modern humans, obviously our ancestors were around longer than that. So modern humans were around for approximately 100,000 years. So our ancestors would have, human ancestors would have met the mammoths and the woolly rhinos. Also, horses started to evolve because of climate change, lots of grasslands to feed on. Okay, so that was quite a brief tour of geological time. Okay, how have you find that out? Hope you enjoyed the video. I hope to see you on the next one. Thank you. Goodbye.